Okay, hello and welcome to my channel. Today we're gonna talk about the virial theorem, which is a very interesting theorem that you will be seeing in these spherical, or like most of the time just central potential thing. So a virial theorem would apply for homogeneous V of R, meaning that your V has to be proportional to like an R of a number, for example L. So virial theorem applies. Theorem applies. Right. Okay, so this is a theorem, so we're gonna be proving it. But first, let's take a look at some form of the theorem that you'll be seeing. V of expectation value of V of t is equal to 1/2 V. T is minus 1/2 V. Other thing is V is equal to minus 2 T equal to 2 bound state energy. One more is T plus B equal to EB. And I think that's it. These are the three common form of the virial theorem that you'll be seeing. So like these two are just the first one, but you just like orient it and just put it in a different way. So they're fundamentally the same. So we're going to try to prove the first one here. Okay, so to prove it, we are going to consider one thing called the virial quantity. I don't know what exactly, but it is virial something called virial quantity. It is denoted as G equal to R dot P. So you might wonder why R dot P, because your end goal here would be to be able to generate your T and your V. And with R dot P, you can see the potential in these two as the derivative of P over time is the force. And in this type of potential, the force is equal to the divergence, the minus divergence of your potential. So I'll write that here. So your end goal is to get V, T and V. So end goal is T and V. So what you can get here is dP dt is equal to F, and F is equal to minus divergence of V for this V. Next is our T. The T is, well, 1/2 mv squared, right? And you can see derivative of R over dr dt is going to equal to V. Okay, so we already got that, and P is of course mv, so we already got what we need. We just have to somehow put these guy back into here, so you can see the ddt appeared. So we're gonna take the derivative of g relative to t, and so we're gonna do that. dg dt, dg dt. Okay, so first I would like to put g in the series form first. So before this, let's say that g is equal to sigma k rkpk. Okay, so we're going to use this instead of the dot product. So derivative, we substitute we put the sigma outside, and we're gonna use product rule. Is my pen so bad? Oh my gosh. Okay, product rule. Take dp dt first so that it looks a bit nicer. Let's dr dt not p. Right, so here you have two parts that you have to deal with. The first part is dp dt, that is the force. Okay, pk. Okay, I forgot I put these in k. Okay, so first part is dpk dt dot rk, that is f of k dot rk, since we can't really expand it more. So we're gonna have to make use of this for now. Okay, so let's move on to the next part. drk dt dot pk. Take drk dt is vk. This is mkbk. So this is equal to mkbk squared equal to 2. Yeah, 2tk. Yeah, 2tk. All right. So these are what you got. Okay, now we put these back into our main function. Fk.rk plus 2t. Okay, right. So we compare this with this. Okay, still doesn't look anything alike at all. So we want to get rid of this. Okay, so somehow these have to equal to 0. Okay, these have to equal to 0. Okay, no, yeah, we by fundamental theory of calculus, the expectation value of dg dt, or here you can say it's the average. The average is gonna be, well, these have to be finite, so we would integrate over finite time. So just to a point k t. Why are my pen dying? Oh my gosh. This is gt minus g0 over t. Okay, this is the average, dt. And this is what you have. And you want this to be 0. You take a limit of t to go to infinity. Okay. Infinity of 0 t gt g0 dt, and this would equal to 0. Okay, so we take a limit of t to infinity because, well, it's sort of like just leaving this outside for a long time to see how it behaves, and it goes to 0. Okay, so with that equal to 0, we can say that we put the bracket for these two terms as well. Okay, so want it to be visible. Okay, yeah, to be visible, sigma k bracket f of k dot rk plus 2 bracket tk equals 0. Okay, finally, we're getting somewhere. Right, so with this, we're gonna have to deal with only the term f of k dot rk. Okay, so we have f is equal to minus divergence of v, meaning that we have write out what we have real quick. Equal to minus divergence of v. We can probably put r. No, yeah. Unit vector. Okay, that's the divergence of v. Next part is your r. Oh yeah. Wait, yeah. This times group this term times r can be split into r scalar and r unit vector, and you have 2 unit vector dot product is gonna equal to 1, so we only have the term so that part is minus r dv dr. Okay, v. So v is in central potential, or in the hydrogen atom that we in effective potential, I believe. Yes, minus ze squared over r. Okay, so the derivative of that is ze squared over r squared, meaning that we have the r here. It's going to cancel with r squared down. You're going to have minus ze squared over r. Okay, so this is just equal to v. So this entire part is going to equal to v. Okay, this is f dot r, not f. Okay, my pen is like really struggling right now for some reason. Okay, so that means we already have what we need. This sum can be put away. Right, so just put it back into a f and r. So now this is bracket v plus 2t. Okay, t, just put it into t, yep. So we now got v plus 2t equals 0. We do the well, you put that over there and then just do the thing, and you would get exactly what we need, which is expectation of t equal minus 1/2 expectation value of v. So now we have successfully proved the Virial theorem, and that would be it for today's video. Goodbye.